Hello, let's talk about section 23.8, acylation of amines. So amines can come in various flavors, primary, secondary, even ammonia. We're not going to talk about the acylation of tertiary amines or aniline. And these amines can be acylated just fine with, for example, the addition of acetic anhydride or acetyl chloride. So if we take, for example, a primary amine and we treat this with acetyl chloride, put a little chlorine here. This is an acid chloride, very reactive. What we're going to form is the amide, okay? The acetamide from acetic acid derivative. So there's HCl produced here, and you know that HCl is an acid. It's going to react with amines, which are bases. So this is the reason that you need two equivalents of the amine for this to sufficiently yield the product, okay? Aniline also can react. So if you have aniline, for example, okay? Aniline is the name of this special amine attached to a phenyl ring. This can attack, for example, acetic anhydride, okay? You can add pyridine instead of using two equivalents of your amine, depending on how precious it is. Pyridine is instead your base instead of the aniline, and this will form an amide as so, okay? So let's look at a couple of synthetically useful reactions here, okay? So here's lidocaine. This is, of course, used to numb the gums when someone's drilling your teeth at the dentist office or other things. And so you can see here that the starting molecule is highly complex. The way to disconnect this is to first form an amine. So we're going to break this carbon-nitrogen bond to give you this alkyl halide, which is just Rx, okay? And an amine. So amines can do SN2 reactions on alkyl halides. Then once you have this, we're going to break here, and we're going to form an amide, okay? So that can come from aniline and your starting acid chloride. So the synthesis involves taking, I forgot the methyl groups there. Let's go ahead and put those in there. We'll talk more about alkylation of anilines. But for now, what we're going to do is start with the dimethyl aniline, okay? And this can react with your acid chloride, okay? The important part is the acid chloride there. And this can be done in the presence of pyridine. Why wouldn't we use two equivalents of this fancy aniline derivative? It's probably expensive, and pyridine is a much simpler, more cheap chemical to use, okay? Actually, I looked at the literature for this. They actually use sodium acetate in aqueous water, and sodium acetate's even cheaper. It's a non-toxic material, okay? So, but we'll use pyridine here on the board. This will make, okay, if you look carefully, the acyl group here, or the amide here on this aniline nitrogen. Then, now that you have this intermediate, you can think about alkylating it. If you treat this with dimethylamine and under refluxing conditions, you can get your product, okay? And that's very efficient two-step synthesis for lidocaine, something kind of complicated here, okay? Another example is fentanyl. I don't want to take you through the whole synthesis and make this video outlawed by YouTube, so we're just going to talk about the acylation step here, okay? Actually, we're not using acetyl chloride, so this is technically not an acylation. We're using propanoyl chloride, which installs the propanoate, okay? So this is going to make an amide with 3 additional carbons there, okay? So if you take this amine, which again is nucleophilic because of the lone pairs, this will attack and do nucleophilic acyl substitution to kick off the chlorine, and you'll get your fentanyl molecule, and we would probably do this with some kind of base added, such as pyridine, okay? So this is generally the last step in the synthesis, okay? So that's how you can get the 3 carbons there, okay? The propanoyl group on there. Tylenol. Now we can talk about this drug in complete detail here. So Tylenol is an acetamide derivative of aminophenol. So this guy here is a sufficiently good nucleophile at the nitrogen atom. We did the aspirin lab and we explained this a bit also in the previous lectures. Nitrogen here is more electropositive. It's not as selfish for electrons like oxygen, which is more electronegative, okay? So the more generous atom here is going to act as the better nucleophile, which is the nitrogen atom, and give you, upon reaction of acetic anhydride and maybe a base added, it's going to give you the Tylenol here, okay? So that's how Tylenol is synthesized. The Tylenol is rarely known. It's all actually taken out of infant medicines now, and there's a lot of safety issues with Tylenol. It gives you liver toxicity. It's very easy to overdose with this compound, and it's generally not a safe compound. Phenacetin, a very close relative, was actually pulled from the shelves by the FDA in 1983 because of safety concerns, and you can see the very similarity between these two molecules. And both of these can be synthesized from phenol. So if you take phenol here on the bottom left and you treat this with nitric acid and sulfuric acid, you'll make paranitrophenol. Now, what you need to memorize, especially for this chapter, is you can make anilines from nitrobenzene using a reducing agent. Iron, tin, there's lots of different things. I use iron and HCl to give you the aniline, okay? And then we would treat this with acetic anhydride, for example, just like we did in the aspirin lab, to give you Tylenol, okay? And this would be one synthetic method for which Tylenol could be made. Now, phenacetin is a close relative. What we need is an ethyl group. We need ethoxybenzene, okay? So here's phenol, and if we treat that with a base, this is the Williamson ether synthesis. We don't need to really use sodium hydride, which is very, very basic. We could just use sodium carbonate or something mild, okay? So I'll just put sodium hydroxide here on the screen. NaOH is a base. That's going to make the phenoxide, which is a good nucleophile, and that will attack ethyl iodide, for example, okay? Iodine is the best leaving group, and that would give us ethoxybenzene. And then we would proceed with much the same chemistry. We would treat this with nitric acid, sulfuric acid. This would give us the nitro derivative as shown with your ethoxy group there. We would reduce this with iron, HCl, and this would give you the ethoxyaniline, para-ethoxyaniline, okay? And then we could treat that with acetic anhydride, okay? A bit of base added, and that would give us phenacetin, okay? So that's been pulled from shelves in Canada, Mexico, United States. I don't know about Europe or other countries. So anyway, that's phenacetin, okay? All right, Tamiflu. Let's get into something pretty big and serious here. So shikimic acid is a natural product produced by various plants and obtained easily from natural sources, okay? And there's a lot of different stereochemistry here, rich functionality. In 8 steps, this is converted to this molecule here in the middle, okay? Now, the key parts here are that the nitrogen has a lone pair of electrons that can become acylated by nucleophilic acyl substitution. So if we treat that with acetic anhydride, we will install the acetyl group on the nitrogen. We call this acylation, right? That's the name of the reaction. And so then you, in another couple of steps, convert it to this salt of phosphoric acid. And that's called Tamiflu. And that, of course, everybody knows what that does. I don't need to say in this time of pandemic. All right? Let's talk about the halogenation of anilines, okay? So I'm going to present this as a problem solution, okay? So here's the problem. The problem is that if you take aniline and you treat this with bromine, you get mono, di, and tri-substituted products. A variety of molecules are produced because the aniline is so hyperactive. It's one of the best electron donating groups. It activates the aromatic ring so well that you get mono, di, and it's just a mixture of things. So people gave up and they said, you know what? Let's just take aniline and treat it with excess bromine, okay, which means 3 equivalents of bromine. And all of these mono and di substituted aromatic rings will eventually give you tribromo aniline, okay? So that is a reasonable reaction. But still, people wanted to monobrominate aniline. How do you do that? So what they decided to do was use an acetylation and a deacetylation procedure. So here's the solution. The idea was to take aniline, okay, which of course has this super highly active nitrogen lone pair because it's so electropositive, it's such a good nucleophile, it's such a good activating agent. And they decided to treat this with acetyl chloride, for example, and this will make the amide. There are various ways to understand why this nitrogen is not as strong an activating group. The easiest way to understand is that there's this electron withdrawing group adjacent to the nitrogen, which attenuates and decreases the nucleophilicity or the activating nature of that nitrogen lone pair. Another way of thinking about it is looking at the resonance structures. Those nitrogen lone pairs are rather busy with the electronegative oxygen through resonance, and so it's not going to activate the aromatic ring as much. Because of this fact, we have a successful monobromination event. If we treat this with 1 equivalent of bromine, we indeed will get the ortho and the para substituted molecules, probably primarily the para due to sterics, okay? So I'm going to draw the para bromo guy here, all right? Now, to remove the acetyl group, we treat this with sodium hydroxide or H3O+, okay? Now, if you're big on memorization, please don't write this as a response to a homework, a question, NaOH or H3O+. Flip a coin and choose one. Either will work just fine to remove that acetyl group and give you parabromo aniline. So let's label these 2 fundamental steps. In the first step, we have acetylation, okay? Acetylation. Acetylation is kind of like a protecting group. It changes the nature of the nitrogen lone pair so that monobromination can occur. And then in the end, we do a deacetylation. Okay? So there's a lot of busy work to change the nitrogen there, but it's the best way to, for example, monobrominate the aniline, okay? So that's something to think about. Another thing is the alkylation of anilines. And once again, I'm going to present this as a problem and then a solution. So here's the problem. If you take aniline, and we treat this with, I don't know, chloromethane, and aluminum chloride, we want to get, you know, methyl aniline or something like that. But there's no reaction that occurs here because the lone pairs attack the aluminum chloride, and it both deactivates the aromatic ring and it deactivates your catalyst. Your catalyst is no longer available, okay? So what you have is the nitrogen lone pair attacking the catalyst, okay? And that kills the aluminum chloride, which is the activator, and it also makes the aromatic ring now electron withdrawing too much so that nothing happens at this point, okay? So remember, when you have a positive charge on an atom right next to an aromatic ring, that's considered an electron withdrawing group. So this is dead in the water. The aluminum can't react, the aromatic ring can't react. It's just nothing happens, okay? So here's the solution to this problem. The idea, once again, is this nitrogen is just too hyper. It just goes after the first thing it sees and it doesn't react the way you want it to. And so the idea is to modulate the reactivity by doing an acylation with acetyl chloride. And this gives you the acetyl group there on the nitrogen, okay? And this molecule now is not so nucleophilic as a nitrogen nucleophile, right? Because you have this electron withdrawing group, it attenuates the electron hyperness of those electrons, okay? And so now we can treat this with just what we wanted. We can treat this with chloromethane, aluminum chloride, and once again, the nitrogen lone pairs is an ortho-para director, so I'll just draw the para product here. So there it is. There's my methyl group in the para position. And then I can do a deacetylation. And once again, you can do that with sodium hydroxide, for example. And that'll give you a nice methyl group at the para position, okay? So that's pretty cool. That's pretty cool. Those are nice reactions, all right? Let's go ahead and do a couple of practice problems here in the book. See what we got. Okay. All right. This is one of those tricky problems that say, okay, that's your only source of carbons, and you got a couple oxygens on there, so you need to somehow convert that to the product. And so the product has 4 carbons. The starting material has 2, and so we just want to think retrosynthetically. How are we going to do this? Okay, that's the best way to do this. Split apart this molecule into 2 components: your amine and then your acid chloride, okay? Now it's logical to see that the acid chloride can come from the carboxylic acid. Okay, we just need to change that chlorine to that oxygen to a chlorine, right? Now how do we make the amine here, okay? Well, it can also come from maybe an amide, okay? And that can come from the acid chloride, okay? So we're going to do a convergent synthesis. We're going to convert acetic acid here into that amine and convert the acetic acid into the acid chloride, and then those two will merge together or converge and give you the product, okay? So this is how I would write the solution to this. We want to take the carboxylic acid, and we want to treat this with SOCl2 to give us the acid chloride, okay? So that's that reaction, okay? And then the other thing we would want to do is take the carboxylic acid, convert this to SOCl2 to make the acid chloride, okay? Add excess ammonia to this to make the amide, okay? And then we'd want to treat this with LAH, followed by water to make ethylamine. Then what we would want to do is mix these two, okay? Substrate A, substrate B, okay? You would just mix them. I would put pyridine in there, okay? And that's going to give you the target molecule of interest. Problem 23, 59 says propose a synthesis, okay? Once again, you definitely want to break this down backwards by using the retrosynthetic techniques that we've learned this semester. So here's your carboxylic acid derivative. You want to break it into two components. One is going to be an amine. Okay, one is going to be an amine, and the other one is going to be, well, there's a methyl group on there, isn't there? So let's draw that methyl group here. Okay, there's the methyl group. And then you want to draw your acid chloride, okay? So now the problem becomes, you know, how do you form this amine? What I would do is, so you have your two choices how secondary amines are formed. They can be formed by reductive amination, or they can be formed by reduction of amides. Here I'm going to choose to do a reduction of amide, and you'll see why in a second. The reason why is because benzoic acids are very easy to synthesize. So here's my amide, and I can break this down into, I'll just put the phenyl there, I kind of ran out of space. Okay, so I could break that down into the acid chloride and then the amine. Okay, and this can come from benzoic acid, which can come from toluene, which can come from benzene, okay? So my synthesis, and that's chapter 19 stuff, so I'm not showing all those little steps from chapter 19. We're already way over on chapter 23, but let's do the synthesis from the beginning here. So we want to make benzoic acid. So remember, that's a two-step procedure. Here's benzene, and we need to treat this with chloromethane, aluminum trichloride to give us toluene, okay? Once we have toluene, we can treat this with potassium permanganate. That's going to form benzoic acid here. Once we have benzoic acid, we can convert that to the acid chloride with thionyl chloride, okay? Now that we have benzoyl chloride, we can treat that with excess methylamine to give us the N-methylbenzamide, okay? So I'm trying to figure out the best way to squeeze everything in here in the writing. So we'll draw H going up this way and CH3 going up that way. And then we can treat this with lithium aluminum hydride. Okay, it almost looks like wrong. Like, wait, what? Isn't that C double bond O supposed to be on the right? Hang with me. Hang in there, and you'll see what's going on here. Okay, so we treat this with lithium aluminum hydride, followed by water. And remember, that's like a molecular eraser that just erases the carbonyl from our molecule. And so what we're going to form is this guy here. Now we need to acylate it. This was the key disconnect that I did at the very beginning. We're going to take this very complicated amine here, okay, benzyl methylamine if you want to call it something, and we're going to treat it with acetyl chloride, a bit of pyridine. I don't want to use two equivalents of that amine. I just spent so much time making it. It's probably expensive. So I'll use pyridine, and that's going to make the target molecule. If you can do problems like this, you're well versed to tackle anything you might ever see in Organic Chemistry 2 in this course. Thanks for watching. This is the final lecture and problem that I will be doing on amines this semester. I'm skipping sections, the latter part of this chapter for my course. So if you do need help, I suggest you read the book or consult other YouTube videos on the last 4 sections of chapter 23. Thanks for watching, and good luck.